Just check. Is it okay now? Okay.
Yes.
Okay. Do I need to submit again saying drop to yo? No.
Hi. Good evening. Am I audible? Yeah.
Still no so. Am I audible now?
Yes, yes. Yeah, good evening, everyone. Thank you for attending this lecture series. This is my profile, but they are already introduced by the president. So let me begin my story, which actually begins with Kenny. Am I audible? Situ. Okay. So this story begins with one of the reconnaissance survey done in Pakistan, where the University of Tokyo consecutively involved with the one survey where they found it some mud flows through the skeleton of the dam and continuously the fine particles being washed out. So resulted in the big collapse or the onset where the dam completely collapsed. So the reason behind this collapse is continuously washing out these finer particles, which increasing the permeability, of course, resulted in the higher permeability and kinetic energy activated, and those particles and the entire dam vanished. So to build the dam, we have the very optimum combination of skeleton particles, that's the bigger particle, as well as the smaller particle. If smaller particle is reduced, the permeability increases. There is a problem of stability. If the bigger particle reduces, the smaller particle are unable to sustain or withstand because of the weight and gravity issues. So this particle is we call as a slaking particle. Slaking particle means if we are applying the drying and wetting cycle, the seasonal cycle, it's get broken, it's dismantled, and particle gradation will be changed. So our research basically try to find what is the optimum of this skeleton to find a particle to make the water retaining structure. Okay. So the slaking particle means which having some clay content. While we are doing drying and wetting cycle, the particle breakage progress, which make the severe disturbance of the particle gradation, which may influenced by the two factors. One is dry wet cycle as well as the temperature. If we make the coupling this with the dry with high temperature and wetting with the lower temperature, exacerbate the progress. And the severe and very progressive, the particle breakage has been observed by the literature. That's why this coupling of this cycle is introduced and proposed by the several researchers to accelerate the seasonal factors. So within 3 years for doing your PhD or 2 years for doing your master's, we can't simulate the seasonal factors for 50 years. We want to accelerate it in the laboratory condition to find the long-term effects of this, the water retaining structure. That's important. So we proposing this coupling effect as well as some of the literature, some other the leading the researchers propose. Of course, the particle gradient is another effect of the void reduction. Because this Dragon cycle happens not on the pre-stress condition, which happening at the stress condition. If any particle breakage happens, definitely particle rearrangement happens, which results in compression. So the void reduction is the part and parcel of this entire change, which resulted the several issues. The increased the shear deformation, where some papers talk about the dam failures, and reduce the permeability. The reduction happens, increasing the water pressure resulted in again the failure, and the particle breakage may cause the severe settlement. But today we don't discuss this. We focus on our tunnel visions on the increasing the point and increase the water pressure, which resulted in internal erosion. That's only our target today to do. So this photo taken by Dr. Danuska in the laboratory setup. This is very simple laboratory setup. No need to have any special knowledge to understand. Just applying the vertical pressure. The hyper pressure. This gravity material applying the wetting, simulating the dam structure. Wetting means not merely wetting, wetting plus hydraulic pressure, and collecting the particle that is washed out with this pressure. At the drying time, we supply fluctuating the dry air with the high temperature and make them dry. And the dry time is the 56 degrees Celsius. At drying time, we kept at 25 degrees Celsius. Why 56 degrees? Normally, the dry wet cycle we proposing 110 degrees in our laboratory experiment. But if we increasing the temperature, sometimes unrealistic chemical changes resulted in showing the overestimating the settlement behavior. That's why we purposefully kept the 56 degree, where that this soft sedimentary rocks is okay with. There is no possibility of having the unrealistic organic related reactions at this temperature. So this is the experimental setup. Applying the water pressure and collecting the particle, the heater, the air supply, this flow chart. And after the 1 and 5 and 9 cycle, we apply the pressure and collect the particle and measure the particle gradation. So the experimental setup is very, very simple. So we did for 5 different the sedimentary rocks. It's very in range of that. If the clay content is high, you can expect the higher breakage. If the clay content is less or 0, we don't expect any breakage. That's the real scenario. So in case of the higher clay content, at the first cycle, collapse happens. The particles excessively rearranged, and the higher pH value resistive to the permeability, and we could not find any erosions there. If it is the no breakage happens at the like metals, where we could not expect, we can't expect any sort of erosion. In between behavior in between material, still having the skeleton as a intact, but developing or increasing the find the way to escape, which resulted from internal. So you can see that the rest of them are almost bare internal erosions, but the material we call the Hamamatsu, it's referring the area where we have collected those, showing the excessive internal erosion around 10%. Okay. So after that, the particle gradation is the most important factor we want to analyze in why this sort of the internal erosion progress. So we did the one more test, changing the vertical pressure. Why vertical pressure? Changing the vertical pressure, increasing the vertical strike. Then void also one of the parts to make the internal erosion or triggering the internal influence the internal erosion. And 100 kPa we already observed the erosion, but 500 kPa we didn't observe the erosion. And we arranged 6 experiments and gone through the same driver cycle, stopping at the after the 1 cycle and stopping after the 5 cycle and 9 cycle, and did particle gradation, and this is how the particle gradation stops up. So in this particle gradation, what we can see by this figure particle gradation, this particle gradation is susceptible and subjected to internal erosion. 100 kPa after the 9 cycle. Rest of the 5 are safe enough. There is no any particle erosion. So what is the internal erosion is another things I want to introduce. Internal erosion is the smaller particle which do not carry any forces or the stresses. It's a free particle that will move to the ocean. So here the particles are applying the water pressure which make them to erosion. So this is the internal erosion. And along the internal erosion, permeability increasing. Along the permeability increasing, the severe collapse could be resulted in, which is recorded more than 50% of the failure only happens due to the internal erosion. The dam. Okay. There is a 2 coefficients we want to discuss about the internal erosion. One is we want to separate both the particle which we call the skeleton. Skeleton means carrying the stress. Another part we call the fine or free materials which are just inside the void. So what we are expecting that this is the skeleton. By this skeleton, the maximum pore-to-pore connection would be D50. Why? We can do it geometrically. If it is the particle gradation, maximum pore-to-pore connection would be D15. It's geometrically proven. I just avoid it, but later we can discuss it how it comes up. This bigger pore, the leeway should be clogged or should be blocked by the highest point. That is the initiation of the clogging. Clogging initiates when the bigger pore will should be clogged by the bigger point. That is the first part to make the clogging. Having done that, the another part comes up. The trapping the bigger particle, bigger point, retain the smaller particle of the point. That is the second part. If those happen, that particle combination is safe. So That what is the very classical, conventional, the coefficients, Tazaki's and Penny's coefficients, which is still using. Our ICTAR book still having these coefficients to ensure it. So still a lot of countries and even US using these coefficients to ensure that whether that particle gradation is safe or not. But what is the major setback or the negative points of this coefficient is there is no place the voids playing the role. They don't consider the voids. So that means whatever compaction it is, it's no problem. Particle gradation itself, the reason of causing the internal erosion. That's not true. But anyhow, our conventional method doesn't care the voids as a function of triggering the internal erosion. So what we can do is, this is the 100 kPa, the 500 kPa. We did the two coefficients. We just developed the two coefficients. Here is the first coefficient. And here is the second coefficient. The D15 over D85. This is H over F. This is talking about the first clogging happens. Bigger pores clogged or blocked by the bigger fines. This one is after happening this, how the small pores, the fines return. So what we can So what we can see that the first one is safer zone. It should be lesser than 5, then this particle gradation are safe. But second one, after the 9th cycle, both of the pressure condition, 100 kPa and 500 kPa, touch the ceiling limit. So both of them should be considered not safer one. It's susceptible for the internal erosion. But anyhow, whatever we noticed in the experiment, this is only triggering the internal erosion. 100 kPa only triggering the internal erosion. So we want to accept that there is some problems with the conventional or the contemporary practicing methods. So let me discuss again how this internal erosion happens again. So if we are applying the pressure here after the particular cycle, the smaller particle would be washed out. The bigger fines, what we found, would be the separation point of here. So whatever the particle bigger than that bigger fine we found here would be called the skeleton. We just take the assumption. Whatever lesser than that, we can call it fine. Then we can do the separation. This is the skeleton particle gradation. This is the fine particle gradation. So in here, we know that the skeleton gradation, we know that we can calculate it because we already have the particle gradation, and we know what is the density of these skeleton particles. By using that, we develop the one virtual specimen in the lab. It's a 3D and it's a 2D for the very narrow range of the particle size. So if it is very loose packing, we can assume it this sort of the way the pores are connected. Pores are always the irregular shape, but pore-to-pore connection always having this sort of the arrangement. In here, it's a denser base, we have this sort of the arrangement. We want to find what is the geometrically the gradation that can be passed by this filter. So we're proposing some new method through the Python where we try to find what is the context. The context means the center to center, the distance. If it is exceed the summation of the radius 1 and radius 2, it's separated. So there is no context. If it is equal, there is a context. Context means load bearing or load transfer could be happened there. So firstly, we try to find what is the context. After that, we try to find what is what are the materials are involving to create this pore. So in here, this pore constituted by this part. So how can we do that? I will explain it. Yeah, here. So there's one algorithm who can use that, the object-oriented algorithm, who has the knowledge of object-oriented. Okay. Depth first analysis that the shortest distance to find the shortest distance. What this our algorithm will do? It will find this is the particle. First we select the particle. It just move it to the shortest angle or the lowest angle of my right hand side. So what will do this algorithm? So it will begin at here. The shortest angle would be 82, 02, and after that shortest angle would be the 11. Shortest angle would be the 11. 30, shortest angle would be the 80, and again the shortest angle of my right hand side would be the 64. So this is the circuit it will develop to find the particles to constitute or develop this pore. So there are two types of the particle we can see here. Two types of the circuits we can notice. One is 3 particle combined circuits. Another one is more than 3 particle combined circuit. So firstly we try to find it. What are the circuits? How many circuits are there? What type of circuits are there? And after that, if it is 3 particle circuits, geometrically we can find what is the particle could be escaped to that pore. Because geometrically, every 3 particle, whatever it is, we can find the one circle to tangent that, 2 circles to tangent that, inside and outside. So in here we are able to find geometrically the one circle that can be transferred to this the circuit. In here, we can't find the one. It might have the several, but geometrically it's not possible. For find a circle to have the tangent of 4, it's possible, sometimes impossible. So what we do is we try to optimize by doing some geometrical operation, which would be the bigger circle can be gone through this constitute arrangement. And we try to find what is the maximum one. So by doing these things, what we can do is we are able to find what are the particle distribution can be escaped through this arrangement, this particle arrangement. So this is the distribution of the particle arrangement, which is representing the red color. What we can get the message from here, the particle bigger than this, there is no way to erode. Particle lesser than this, there is no way to retain. The particle in between, the probability of this area would be the passing. This area would be the retain. Probabilistically, we can say that. So here, for the explanation, we did the same size of the particle, but realistic case, it's more complex. This distribution would be almost the normal distribution. Okay. After that, we make the pore distribution, virtual pore distribution. What the virtual pore distribution? We assume it, pores are arranged in a cubical way. Every pore having the connection of 6 connections along their faces. This connection distribution will be same as this distribution. That's why we are working on it to find this distribution. This connection will be the same of this distribution. Okay. Then we have the fine particle distribution earlier. No? We have the fine particle distribution here. We have the fine particle distribution. We equally placed all the particles in this pose. After that, this is what like the puzzles of finding the escaping route. So if the particle able to find the escaping route, we can call it as a escape particle, so eroded particle. So what are the constraint it has? This particle should be lesser than this constrictions for the pathway. That's the one and only condition. No, there is one more condition is this pressure should be higher than this pressure. Otherwise, particle will not move. So another problem comes up. How can we define the pressure of this force? Otherwise, we can't do the simulation. We can't do the simulation. So find the pore pressure. It's so popular one. So this is what we discuss it here. This is the constriction. That means the base dimension distribution. This is on frequency. This is on frequency. That means number. This is the fine distribution. This is representing the mass, weight, not the number. If we make the number, it will be very big. So that's why this simulation unable to do with our normal computer. It will be the very huge number it will come. So again, we just go with that, how we can calculate the pressure. So we know that it is the 2D, but actually it would be the 3D. Now one pole is connected only with the 4 connection, but the real case, in our real simulation, it would be connected to the 6 cases. So the flow on this 4ij, net flow would be 0 because earlier it's saturated, now also 100% it's saturated. So the continuity equation we can apply. These continuity equations we can write like this. It's all of them are known factors. RC4, we already developed the distribution, we already developed the dictionary where we can get that constriction size. And these all the factors are known factors. What is the unknown factor? The particle, the pressure only is the unknown factor. Every pore, we can develop the one equation. So we have the number of the pore is only unknown factor. Same number of equation we can create. So in our case, it has the 40,000 pores. So we can develop the 40,000 the equation. So what we can do, 40,000 equation, 40,000 unknowns. So we use this fast matrix, and it's these sort of the works the Python is eager to do. We are able to find the pore pressure distribution. So this is the how our pores are looks like, and this is the top view, and this is the zoom view of some particular portion. So where the constrictions are the distributed like this. And then this is I try to explain how we can come up until this point. And we do the simulation. So we developed the one algorithm where this is the threat, more the fine particle, which will be checked which way it can find the higher water gradient. That means the leisure pressure. If it is fine, this one is the leisure pressure one, this particle try to move this way. At the time, it will check whether this path is enough to go with or not. If it is not, it will check the second gradient path and third gradient path and fourth gradient path. Ultimately, it could not find any way. Then we call it the clock pose. That this pore will not be participating or take the part to transfer the any particle further. If this particle find the way to go out here, we can call it the eroded particle. Then we try to make that numbers, representing the numbers. Always, this is very high number, 1.6 into e to the 7. High numbers. We do the very high simulation. Every particle want to move here, here, here in 40,000 pores. It may have around the 4 lakhs movement. So every particle should have the 4 lakhs iteration. The particle numbers is E7. It would be very huge. So we can't do it with our computer. We invoke some supercomputer to do these erosions. So what we can found is the rest of the particles showing the clogging. There is no more particle washout happened. It seems to be flattened. But the 100 kPa where we found the high erosion showing the increasing the particle washout along the time. Increasing particle, which showing some relations qualitatively. This erosion could be explained or interpreted by our simulation, but not quantitatively because of this clogging is little complicated, that one. So unable to represent one-to-one quantitative one, but qualitatively showing the good relation. Later part, we try to make how these seasonal factors have the effect of the internal particle to causing the breakage. So we took several assumptions and make the DVM simulation on the single particle. For the single particles, a bonded particles having the 9 influencing factors. But to have some assumptions, we reduce it to 3, that all of them are having some strong logical backgrounds. So this is what the internal particle, the stress behavior. If it is inside, that is the bonded particle. If it is moving this way, we can say that tension failure happens. If it is moved this way, we can say that shear failure happens. Okay. So we started with some empirical relation of 3 parameters. That means K, which is rely on the Poisson ratio, and another one is E, which rely on the stiffness of the particle, the specimen, and another one is that the cohesions, which rely on E and K. So with this initial parameter, we constitute the specimen and check it whether K, we initiate the K and measure the Poisson ratio. The whatever we measured in the experiment and measured in the simulation, if it would be the equal or less than 0.5% variance, we continue it. Otherwise, we increase the sum amount. of additional one. Same thing we do. We develop the one algorithm. Otherwise, it will take a lot of time to do this, because how this increment happens. So several researchers they're discussing about how this increment happens. So if we do the high increment, we could not find the sharp point. If it is do the very small increment, we need the higher computer power. So for example, this is how we work. We make it this one, change it, and make the simulation and measure it in the laboratory and compare it. So we make the, for example, we just take it. This is the real relationship. We don't know. We don't know. This is changing with the different material. This is a real relationship. But this is the empirical relationship for the some other material. There are a lot of material they have developed. For this, we want to measure, we want to do at least 100 tests to make this behavior, make this the relationship. What we can do is, this is a target value from the testing. We just project the target value, what would be the value we want to set for the simulation, and do the simulation, and we can find it. This is what the simulations offers us. But this is what we are expecting. Then we shift the empirical relationship to this point, and we do again. We just project this one to here. This is what we are expecting, and do the simulation. But this is what you observe. So within 3 simulations, we are able to pick up the very accurate point by doing this, the optimum finding algorithm. We are able to pick up the only 3 simulation needed. Otherwise, it's required the more simulation. One simulation requires at least 1 week. So this is how it works. So this is the experimental one, and these are the calibrated parameters for the DEM, and through which we are able to make the bonded particles. These bonded particle inner properties are related to the dry specimen properties. So while in here you can see that the green one are the linear bonds. There is no any cement in between. But the blue one are the cement bonds. The cement bonds are representing in these conditions. After that, we do the loading. While hyper pressure, while under the loading, we change the properties gradually to the wet conditions. So we already measured in which way the intraparticle, the circulation happens. With that time, we try to reduce the particle properties here to here. So then the stress condition at here would be collapsed. So there is no more cement bond. So you can see here, this is the earlier condition. This is how the linear bonds are available. After changing the properties, we can see that there are a lot of linear context. That means the cement context changes to the linear context. Again, how we can measure the particle gradation? Because we have the particle gradation at the laboratory. How can we measure the particle gradation? It's another challenge. We should find what are the clusters having the cement context, what are the clusters are not having the cement context. We call it as a transportation matrix. By running this transportation matrix, ball 1 having the cement content with 1 and ball 2. Ball 2 have with the ball end. So we can collect all the ball and ball 2 ones. These are transportation matrix. We collect all the clusters, and those clusters can be drawn like this. And after that, we rotate it. We should find the sieve size. What's the sieve size is? We should rotate it small. we should find it. What is the minimum projected thickness? So if it is this one, this is the projected. That's what we call as a sieve size. So we just make the sieve size for both. This is the simulation how is after the applying the pressure, we just slowly change it, then we can see that how the particle breakage happens. This is for only for the presenting, but our model is little big, unable to show. So this is the particle breakage. What we found in the laboratory one, what we found in the simulation, having the striking similarities, not only in terms of particle size, but also the inducing the vertical strain. So that's all. Thank you.
Thank you, Dr. Nihaaj. And it was a very interesting and very uh, informative presentation. I'm sure our audience may have a lot of questions to get clarified from Dr. Nihaaj. And I invite the audience to raise any questions you have about this presentation. This you can, yeah, you can come in.
Can take models. So in earlier case, we don't consider any contact models, but no need for that. In here, we make the linear context. This is what the Siemens context, especially design context for the particle flow code. So the Siemens context means it will not active until it will be collapsed. Putting the pressure from top. Inside the particle, we can measure it. So inside the particle, we just notice every point, we just every milliseconds, we just notice what is the stress condition of this every point. So if the stress increases, if it exceeds its capacity, like this, if it is exceed the capacity, it's fair. It will make the tension. In this way, it will be the shear phase. After that, it's a linear context. It has there's no more any Siemens context. We normally do the Hertz context. Context. Yeah. We don't model the context, but we try to calibrate how this context would be assigned for the different material properties. What we can measure in the laboratory. With that properties, we can assign the internal properties. Because it's what very difficult, most challenging part the PFC or the DEM is how we can make the internal parameter. That's why the bonded particle and particle breakage is not so popular in DEM. DEM normally make the particle flow and the rock falling. Those things are very detailedly analyzed by the DEM, but not the internal particle behavior, because the calibration is so difficult. So we try to proposing the new method calibration to make it a little simple. Thank you. Yeah. So Have you got it up? This is what our targeting value. We try to make the simulation targeting value. This is what the empirical equation. We take the microparameter. By this microparameter, we make the model and do the experiment and measuring what is happening in the simulation. If it is this one is the height, we just repeat it and repeat it until it make specific similarity within our scene, within our range.
How do you check the water drainage of the problem?
Yeah. The DEM to do the water and simulate the water is very, very difficult. So that's why what we are doing is it's little innovative approach. What we are doing, firstly, we calibrate the properties of what is wetting, what is drying in the properties. And we assume it, there is the water. Then the internal property will be changed or reduced. So we don't use any water particles. We don't use virtually it's water, but we don't use any water particles. We only do the calibration for particle breakage, not the erosion. Erosion we can do it. How? There are several ways we can do the erosion, but I didn't show these. If it is there any particles, free particles, if there is free particles, we don't have the context, we can make the same simulation in body, but not with the water pressure. Because almost impossible to use the water pressure and water for this small model. Need a very huge model and huge amount of the machine power. We just simulate and mimic the water effects, not the water. Yeah, the big calling. That means every microsecond, we just monitor this context. And context study. If it is exceeded, not every microsecond it will find which will. So it's normally works on the Newton law. Whether it's applies some forces, it will move. If it is not, it will be there. Yeah. So normally it's not the one particle. One particle representing 1,000 particles. It's not the one particle. It's representing the 1,000 particles. Internally, every stress will be calculated. These are small moles of one particle. Every particle representing by the 1,000 particles. Every
one particle is like a funny.
Yeah, not fermionium. It's constituted by 1,000 particles. Every particle has the bond. So if it is exceeds, that bond broken, and this particle breakage happens.
So it breaks pieces.
Yes.
Means thousand, so it can be.
Can be 20, 200, 400, 300. The particle linear contact to linear contact. These are linear contact. Earlier cases linear contact. Yeah. Internal shear stress. The particle have.
Yes, so that means even consist of 1,000 particles, so generally it can shape.
Here, after the Steven bond,
Your particles are spherical.
internal particles are spherical. Our particles are the good shape,
Yeah.
real shape. But internally, it's constituted by 1,000 spherical particles.
Thousands is spherical, but
That it constitutes the almost irregular particle, almost real particle.
how it cleans the clay particles are plate shape.
Yeah. But here, sir, we are representing this behavior for the gravelly mudstone particle. It may have some portion of clay content, but not the clay particle. Yeah. Yeah, we just take the photos from it's separated and take the photos, and we just make the particle shape with the distribution. We just take the 60% confidence distribution and choose all the particles. It's almost 20 type of the particles we created. We just move on little logical way. Otherwise, if we make the lot of particles, the model would be very complex. So in the last portion also very problematic for us. It is separated like 200 particles in one way, 3 particles in one way, 50 particles in one way. We should make that the clusters, should find the clusters which have the relationship with which particle. That is the one of the major part to do the C1 analysis.
The impact of this 5 feet
dry wet cycle, but we stop it. Don't have the time. We just stop it with the cycle. Don't put that after that. We don't go. We can do that. We can do that. Yeah. After that, we want to do the calibration earlier. What will be happen for the second cycle? Here we do only calibration for first cycle. So we do what we do. We want to do the calibration. What will happen after the second cycle, third cycle, and fourth cycle? I think it will take the long story. Yeah. Any question from the online audience today? Yeah, they are talking, but they already muted it.
Any question from the online participants? Can put there. We can check. There are 8 questions. Online participants can raise their questions through chat box. Mute කළදී අපි නැහැ. නැහැ. chat box එකේ නේ. There's no need. Any more questions? Any question from Professor? Ask it. Yeah, we have another successful geotechnical forum. I am very much thankful to Dr. Nihaaj for his contribution towards this geoforum. And also the topic is a little bit modern and not very familiar topic, but I'm sure that people got some idea about the about this presentation. And I would like to appreciate again Dr. Nihaaj, and shall we pay our appreciation in usual form. Okay, thank you. Maybe speak it.